Okay, we are live, folks. Welcome. This is Connected Devices, and this is the review for quiz number 2. This is the part 2 quiz, which means that I'm going to cover classes 3, 4, and 5 as quickly as I can. Of the class, but it's really close. So we're going to get started and dig into class number 3, and then we'll go into 4 and then 5. And so what I'm going to do here is cover the lecture content and then also talk about the implementation exercises and so forth. So you will see that there's a bunch of additional content, things that I've tweaked since the last time I actually presented this content, and I'm hoping that this will resonate even more so. So stay with me, please. Keep your YouTube channel pointed to this channel, your YouTube connection pointed to this channel, and we'll go through all of this awesome stuff. Again, this is Connected Devices. This is part 2, data and integration. It covers classes 3, 4, and 5. Let's get started. Okay, class number 3 is all about sensors and actuators, but not real sensors and actuators, although I'll kind of talk about the real ones. We're mostly focused on simulating the sensors and simulating the actuation events using simple log messages and whatnot. And then we're going to get into emulated sensors and actuators in class number 4, and then how we bring all this stuff together in class number 5. Let's dig in. Okay, about sensors and actuators, recall from the lecture content, I talked about the Industrial Internet Consortium and specifically the IIC's reference architecture. This is a very useful document to have available, as well as the IIC's connectivity framework. These are really great resources for all of you as students to be aware of and to be referencing as you pursue your studies, and that's no different for this particular class. Remember that we talked a lot about something called functional domains. And so we've got this thing called the control domain, which is really focused on the edge tier specifically. And so what we've got are things like actuation and sensing that are part of the control domain, as well as modeling and asset management, as well as communications and even abstraction of different types of entities, which is big part of what we're doing in this class. We are creating abstractions around things that would normally physically exist, but in this class we are virtualizing everything because frankly it makes things a lot easier for us as software developers, and certainly from a distance learning in class, remote class kind of presentation perspective, it also makes it easier for us to demonstrate things and whatnot. So recall that again, we've got our logic, we've got our abstractions, we have our communications in that control plane. We also have our sensors and actuators. These can technically be distributed across different physical systems. Although most of this, not all, but most of this will actually be living within our constrained device. Some of the stuff will certainly live in our gateway device, including the modeling capability that we'll be talking about. All right, so what is a sensor? What is an actuator? Let's dig into these individually for just a few minutes each. Remember, sensors process input data. They're readers, really. And more specifically, they convert mechanical energy into electrical output, something that you can then interpret within a computer. There are certain considerations that are important to keep in mind, including calibration and the range, the floor and the ceiling. These are things that we need to understand about a sensor because it provides context. It helps us understand what the sensor is capable of doing, and just as importantly, what values are relevant and which ones may not be. What are some examples of sensors? And I've got a couple of pictures here. These are both taken from my home. One is actually taken from the shed on my house, and this is a water level sensor or rain gauge. Basically, you can see in the center, it's got a tube with a bunch of slots in it. If I turn the top, it actually opens up a cover that's in front of those slots and allows the water to drain out. And all this really does is it gives me the ability to manually control how sensitive it is to rain. You'll see the antenna hanging off the bottom of the first tube, and that provides a very simple wireless signal to the control panel, which is bolted to the side of my house and actually will receive that signal and determine whether or not it needs to activate the valves via actuation to enable the sprinkler or the irrigation system to engage or not. So it's all driven by water pressure and then small low voltage to actually open the valve or close the valve, but it's based on whether or not this rain sensor is saying, hey, there's enough water or there's not enough water. So it interprets that signal and makes a decision. The sensor doesn't do any of that. It simply sends a Boolean. There's water, there's not water. That's it. It doesn't care what the controller does. Okay, now on the other side, we've got something called a Sense Hat. The Sense Hat is something that some of you have already decided to purchase, and that's awesome because it will provide you with a lot of opportunity to experiment if you're running it on a Raspberry Pi. This particular device contains a number of different sensors, including humidity and pressure. And by the way, you can derive temperature from both of those sensors. It also has something called an inertial measurement unit, which provides the ability to calculate orientation. There's an accelerometer, there's a magnetometer for compass readings and so forth. It also has an LED matrix, which I'll talk about in the next section. Actuators handle input data as movers, and they actually convert that electrical energy into mechanical energy. So actuators are actually the converse of sensors. Sensors take mechanical energy and convert it into electrical. Actuators do the opposite. And that's really important because at the end of the day, we probably want the ability to not only read a bunch of stuff coming from the physical world, but we probably want to do something with that, and maybe even flip an actuator, flip a switch or something like that, or turn a valve on or off like I just mentioned we would do in the irrigation system. So these tend to work together, but they are independent. And so I need a controller that will basically read the input signal coming from the sensor, figure out what to do, and then trigger an actuation event. Now, something I mentioned in class number 4 is a process called hysteresis. Now, this is where we've got a bunch of signals coming in from our sensor, and we are performing a leveling, if you will. We're basically waiting for something to happen before we actually take an action. And the reason for that, I'm going to talk about it more a little bit later with some examples, but the reason for that is because we don't necessarily want to react to every single sense value that comes across the wire. Sometimes we want to wait for a little bit. And again, I'll talk about that in a little bit more detail later. Here are some example actuators. You can see that on the far right-hand side, we are looking back at the Sense Hat again. This is the LED matrix that you saw just a moment ago, and it actually is really just the boot sequence, but you can see it illuminating in 2 different patterns. There's actually a couple of different patterns, but I can send a message, an electrical message, to this LED matrix that it will then convert into mechanical or light energy and show some kind of graph or some display or scroll characters or something like that. I can use that as an actuator. Likewise, in figure 3.4, I can actually trigger a valve to either engage or disengage, or rather open or close. But with this particular example, I'm actually spinning something called an impeller, which is just an internal propeller, really, that rotates and actually pushes water out, whereas a propeller on a plane will actually pull air across the fuselage and the wings and so forth to help to generate lift, and actually moves it forward and so forth. And as it moves forward, the wings, of course, generate the lift, which causes the aircraft to fly and so forth. In this case, we're not causing lift. We are simply moving fluid through a system. And the purpose of this is to receive a signal from a thermostat, and then the controller unit, which you actually see that blue kind of robot looking thing sitting at the bottom right hand side, will interpret the message coming from the thermostat and say, hey, you know what? I have to tell this circulator pump, the red thing in the upper left corner, to start spinning its impeller to move the water that the big blue thing at the bottom is heating up through the heating system, or in this particular case, through one particular zone. zone in a heating system is really just a cordoned off area that has a dedicated circulator pump associated with it, or perhaps a single circulator pump that pushes water through the whole system, and then valves that actuate for a given zone or turn or close off that zone. Let's look at two different scenarios from an architectural standpoint. We just looked at physical hardware. Now we're going to look at a logical depiction. Figure 3.6 shows a smart thermostat, which is actually not including a constraint device. In this particular example, I'm just showing a gateway device that happens to have both a temperature sensor as well as the ability to send an actuation event to a controller. Let me just pop up my Teams view right quick here. Okay, everything's good. And so what this is showing is an example of something that you might have seen in other smart thermostat systems where the entire thing is bundled in this one package. It connects over Wi-Fi to your Wi-Fi router, and from there it can communicate with a cloud service and provide the streaming data, if you will, to that service that you can then interpret and even use your mobile phone with the appropriate application deployed to control that smart thermostat remotely anywhere in the world that you have an internet connection. On the right-hand side, we've got something similar, but this is reintroducing the constraint device. And in this particular case, I'm actually showing how you could trigger a door lock or the deadbolt on a door lock that's controlled by a servo. And that servo is just basically a motor that has some logic, and it knows exactly how much energy to push to close, or rather to return the piston to push that lock into its appropriate place and maybe pull it back out again. And so this is something else that at the cloud tier, I can render, or I can actually implement almost identically to what I'm doing for the smart thermostat, but the implementation at the edge is very different, and the commands I need to send are different, of course. Here's just a quick picture of what that might look like. You've got your thermostat on the left-hand side, you've got your actuator and the valve on the right-hand side. These two work together. I'm not showing any cloud service here, but you get the picture. And here is what it looks like in a little bit bigger view. You can see the door. Oh, this is the wrong picture. Sorry about that, folks. Well, this is what it's showing. Actually, this is the picture for this particular thing. So this is the door lock controller. You've seen the thermostat one already, so I don't need to rehash that, but let's look at scenario 2. This is the door lock controller. Notice that I've actually got a Raspberry Pi that's serving as my gateway device with a Z-Wave dongle, USB dongle connected into it that then communicates again over Z-Wave. Remember, that's sub-gigahertz, right? To the door lock controller. This is a motorized door lock. It has a servo built in that when it receives the appropriate signal, encrypted by the way, via Z-Wave, it will then engage the piston that will then lock the deadbolt, or rather push the deadbolt in out, or pull it back in again. So I got these pictures reversed, sorry. All right, let's look at some other examples real quick. You can check out these links on your own, of course. There's some really interesting water quality sensing and monitoring work that's been done by the University of California at Berkeley. You can check that out at the link below. There's this structural integrity monitoring capability. There are a lot of companies that do this kind of thing. This is just one example, a company called Smart Structures that actually provides embedded sensors within structures so that can determine load and strain and so forth and so on. You can check out their link and get a better idea. These are just examples, that's all they are. And then again, for home automation, here's one more example. There are plenty of these, but this is referring to the Google Nest, which is a smart thermostat. Some of you may even have this in your homes. And that is something that, again, represents basically what I just talked about for smart thermostat capability, giving you both sensing and actuation capabilities built into a single unit. All right, so that's it for this section. Now let's blaze ahead to sensors, actuators, and data generation. All right, so how do we generate data? This is where I'm going to talk about data simulation. So working with real hardware, as you can see from all the stuff that I've been talking about, can be challenging because every single one of those hardware components has its own unique characteristics. It's got things that it can do, things it can't do, etc. And we need to know exactly how to talk to that, which means our software has to be specially designed to work with that particular platform. So we'll simulate the data instead. And that doesn't mean that we're taking anything away from it. We are actually trying to do as good a job as possible to represent exactly how that device behaves. So what does that mean? That means that we need to kind of model, we need to create like a use case, if you will. So going back to our rat, which is that one use case I introduced a long time ago, we have temperature, pressure, and humidity. We've got values that we need to represent to provide a temperature range, a pressure range, a humidity range, etc. Right? We also need a way to put that data into some kind of structure. So let's take a look at how that might look if we were to graph it. You can see in figure 3.6, this is an indoor temperature range. In figure 3.7, this is a typical range for humidity. In figure 3.8, this is a typical range for pressure. So what does this mean, and why are the lines all weird like that? Well, this is just noise. So the data generator that I'll talk about next provides the ability to apply a noise percentage. And it's just my own percentage that I introduced to try to keep things within a reasonable range and so forth. And basically what I'm showing is that the indoor temperature range for every single one of those values can fluctuate quite a bit, as well as pressure. But humidity, because I just chose this particular range of noise, or very limited range of noise, the fluctuation between every measurement is actually very small. What does this mean? Well, this means that you actually have something that might represent a more or slightly more realistic representation of the values that you might be getting from a temperature gauge or temperature sensor, humidity sensor, pressure sensor, etc. The way you use this is by the sensor data generator class. This will batch the values and the timestamp into a single class that you can use to pass into your sensor tasks in order for them to simply pull out the latest value and return it back to the caller. So the whole idea here is to provide a very simplistic way for you to generate a large range of time series data that you can then use to test your system without having to connect into actual hardware. And so I think you've already done this and so forth, but it is important, especially for the quiz, for you to be aware of the different capabilities that are part of this particular class. Talked about this, you know that it generates a sensor data set, which gives you an index, if you will, into time as well as the value itself. And you can override these methods in your own derived class, or you can derive it and create or rather you can instance it within your own separate class and create your own methods as well. It's totally up to you. This is just a tool for you to use if it is helpful. Here's the stuff that's more important, although certainly generating data is pretty relevant for our purposes. We have 3 different classes. We have sensor data, actuator data, and system performance data. Remember lab number 2? Right, so system performance data is a representation of that in a single structure for CPU, memory, and disk utilization. Now, all of this stuff is good, but because they're going to share a bunch of common properties, it's helpful to have a base class that they can all derive from, that is like the parent class, and it contains all of this awesomeness, including a name or an ID, which we're gonna need for context. We need to kind of know what the device or the sensor is, right? Right. We also need some kind of ID, which makes it easier for us to use a switch statement. Now, we don't really need to include a type ID. What we could do is just say we're going to map the name to a type ID in our own logic using a configuration file, and that's fine. But I decided to just include it here within the base class itself as a convenience. The timestamp is going to adhere to ISO 8601 format, and that's really useful because we know, being a standard, most other systems that understand ISO 8601 ought to be able to parse our timestamp. And so this adds to the ability, adds to our compatibility capability, right? So that means that when we convert this into something that other systems can understand, then when they receive the timestamp, well, by golly, they should know exactly what that time is, right? Right. Okay, now the next thing is a status code. Now, status code can be a wide range of integer values signed, so they can be negative or positive. Now, what are we doing with that? The status code for all of the stuff that we're generating right now is going to be largely determined by whatever we decide it should be. And every sensor may actually have its own set of status codes and even those that represent error conditions. We're going to go with the idea that everything less than a 0 is an error condition and everything from 0 and above is not. And that means that in the base class, we can actually use that to determine whether we set the has error flag to true or false. So what happens here within the base class right now is if a status code is set that falls below 0, then the has error flag is set to true. That's just a convenience for us. Again, it's not something that absolutely must be there because we can just look at the value in the status code and make that decision on our own. But it's kind of nice to have that context. It provides us with a little bit more richness in the data and so forth. But again, it's completely optional. The last thing though is not, and this is really, really important because at the end of the day, we kind of need to know where our stuff is, right? So that means that we need to know where the location of that thing is. Yet in some cases, we may not be able to easily get the latitude, the longitude, and the elevation in meters or in decimal representations. And because of that, it may be helpful to have a location ID represented as a string. And so this could be something like my house or home number 22 or factory 4 or whatever it happens to be. These are things that we can use to help map an object or a thing, a sensor, if you will, to a particular location. And we can use that to then map it to a geocoded space, latitude, longitude, elevation, for example, even if we can't derive it within the actual message itself. For our purposes, we're going to include both, but I'm actually okay with you just filling in the location ID for your projects because for our purposes, that will actually be good enough. All right, I'm sure you're wondering, like, doggone it, we talked about this before. Aren't there standards? In fact, you told us about some standards, and you would be absolutely right. There are standards for this kind of thing. And these standards are actually very important, and you should understand them. I'm going to reference them a little bit later in class number 5, or right before class number 5. The thing is that they're also pretty involved, and yeah, they're really, really important to know, but I actually think that for us to learn more about standards and why they exist, creating our own can be really, really helpful. It's a great learning experience. And frankly, this is going to help you understand the nuances of converting your data into something called JSON or JavaScript object notation. And this is a really important data formatting scheme to understand because, well, first of all, we're going to use it pretty heavily within this class to communicate between not just the constrained device app and the gateway device app, but also with the cloud and back again. And so JSON becomes a very important construct to comprehend, and the ability to convert objects into JSON and back again is going to be equally important. We'll talk about that in class number 5. And by the way, this is also going to be fun and we can do it, so why wouldn't we, right? Well, okay, that's maybe not the best reason, but it's a great academic exercise and we are in an academic institution, so why the heck not, right? All right, let's move on. Building a simulator. How do we do this? Well, you can do it yourself by implementing lab module number 3. Using some of the existing code that I've already provided in the Python components repository. And by the way, you're only building out the constrained device application for this particular lab module. Let's take a look. Notice that we're making minor modifications to the constrained device application and also the system performance manager. But here's where things get a little bit different. Notice that we have this new thing called device data manager. It's like, oh my gosh, what happened? Constrained device app used to talk directly to system performance manager, but now we're changing things up. And we're doing that because we've got a really good reason for it. We wanted to get things working very quickly with the understanding, by the way, that we would introduce a tiny amount of technical debt in class number 2. And that's all right when we understand that that's the purpose behind it, is to get things up and running quickly with the understanding that we would make a change, and in particular, knowing what that future change is going to be. That's not necessarily a bad thing. And so what we have here is a switch of roles. So Device Data Manager now takes over for what System Performance Manager was doing, just from an instantiation standpoint, not functionally. And so now Constrained Device App talks to Device Data Manager, and now Device Data Manager creates and manages the instance of System Performance Manager, as well as Sensor Adapter Manager and Actuator Adapter Manager. And these two new components will manage their own tasks. Sensor Adapter Manager is going to manage threaded tasks or scheduled tasks that will read humidity, pressure, temperature, and frankly, whatever other sense values you want at a regular interval using the AP Scheduler library, which I reference in our examples and in the online GitHub repository and so forth. And then the Actuator Adapter Manager is not going to fire up threads. It only needs to react to messages that are being sent to it from, you guessed it, Device Data Manager. So all this stuff feeds up to or from Device Data Manager, which eventually will also talk to our connection infrastructure when we get to part number 3, which is actually later, but not right now. So with that being said, the Device Data Manager is now our orchestration engine. It manages all of the messages that are flowing throughout our system. Constrained Device App is basically just pretty happy saying, hey, Device Data Manager, I'm going to create an instance of you and you do all that magic, awesome work. And Device Data Manager says, yeah, I'm good with that. I'm going to do all this awesome work, and I'm going to have all of these other components do their own awesome work. They'll let me know through this thing called iData Message Listener, which, by the way, should also be yellow, but I forgot, so it's not. Sorry. Anyway, that is just the interface that defines the callback functions. A callback function is nothing more than a regular function that happens to get called back to. That's all it is. It just has a defined signature, so we know that, hey, it takes these 2 or 3 or 1 parameter, and it happens to be called by one of these other components that Device Data Manager owns. They just are operating on the iDevice Data Manager or iData Message Listener interface. They don't really care if it's Device Data Manager or something else that implements it. In Java, this is enforced. In Python, not so much. In Python, the way I've implemented it, just for convenience sake, is not using a meta class, but actually just defining iData Message Listener as a base class. That's all it is. That has no implementation behind it. All the methods pass, and then Device Data Manager inherits or extends that base class, which I'm using as an interface, and implements those methods. So that's kind of how it's designed. You've seen all this stuff, so we don't need to go into detail here. You know how to access the GitHub repository with all of the requirements and whatnot. And folks, that's it for class number 3. Let us blaze ahead and jump into class number 4, where we'll talk about emulating systems and a little bit about GPIO and circuit protocols. All right, so this class is still focused on the constrained device application. We will not get to the gateway device application until class number 5. All right, so about constrained devices in general, I think it's helpful to understand how to disambiguate between different types of constrained devices, and then we can use these definitions that are already in place to help understand what our own constrained device application should do and how much processing or not it will have access to. So take a look at the reference below. This is IETF RFC 7228. This is the terminology RFC for constrained node networks. Again, RFC 7228. I believe it was last updated in 2014. So there are some things that may be changing in the future, but for right now, this is still a very good representation of what a constrained device is. Now, for our purposes, constrained simply means limited in comparison with a typical computer. A constrained device will have limited CPU or memory or power demands. In an IoT context, it will usually, not always, but usually have some sensor or maybe an actuator attached to it. They can communicate, otherwise it's not a very useful computer, but probably limited to local area networks. And at that point, depending on which type of device it is, it may even be limited in terms of how it communicates over that local area network. It may not have IP access. In fact, class 0 devices listed below here are very constrained. Kilobytes of memory, they can't communicate directly with the internet, meaning they probably don't have an IP stack built in, which means, well, okay, even if they can talk internet protocol, they probably are not designed to do that. And so they'll usually use a different type of protocol to communicate in a very constrained manner with an other type of device, like a gateway device. Now, class 1 devices expand upon it. They build upon a class 0 and can actually introduce the ability to talk over an IP-based network. And class 2 expands upon that even further, still limited, but does have communication capabilities similar to what you would see in a laptop or in a tablet computer. And I'm not talking about your multi-thousand-dollar gaming rockstar computer laptop. I'm talking about a typical laptop computer that can actually communicate with the internet or talk to a set of Bluetooth headphones or whatnot. So we might have a couple of different radio capabilities built into a class 2 type of device. We're going to assume that our constrained device application would run typically on a class 2 or above constrained device. Emphasis on above. What types of hardware might you see in a constrained device? Well, there are things that we got to actually consider for a constrained device and even for a gateway device, but let's focus on constrained device first. Things like the physical container, the chassis, how it's actually protected. The physical chipset is protected. What is the power subsystem? Is it going to run off battery or is it going to run on line power? These are important considerations because it ultimately impacts what types of communications system may be viable. If it's purely battery oriented, then the communications subsystem will be designed around that most likely, because you can't just be blasting out telemetry data every couple seconds over a high-powered transceiver that communicates with a network that requires a high-powered transceiver. That doesn't make a lot of sense for a constrained device that's running on battery power. The battery would be humongous, right? So there are things that we need to consider in terms of how often do we send data, what types of connections do we actually have, what type of radio are we using, what type of communications paradigm, what spectrum is that radio communicating over, etc. Right? These all inform things that would affect the power subsystem. The processor does as well. Is it a system on a chip? Is it a microcontroller unit? Is it FPGA, which probably not, but maybe an ASIC, or is it a general purpose processor? Right? These are things that we have to consider. Maybe if it's super low power, it'd be an ASIC or an ASIC design or an MCU built on an ASIC. But generally speaking, we may not be using a general purpose processor if we're really concerned about power and whatnot. And then of course, we do need to understand what types of sensors and actuators we might have and what kind of power draw those particular devices may have on the system. Here are some kits that you might want to consider. By the way, these are not all constrained device kits. Some of these are just gateway device kits, but you can take a look at some of them, and certainly things like Raspberry Pi is very popular and common and useful. In fact, I've got two right here. I have a Raspberry Pi 0W and I have a Raspberry Pi 4 in an aluminum chassis. This, by the way, is a 4-core processor with 4 gig of RAM and runs at, I think, about 1.3 or 1.4 gigahertz. I forget exactly the spec, whereas the Raspberry Pi Zero also supports, they both support Wi-Fi, by the way, but this is a single core and it runs at about a gigahertz or so. Now, there's also something called Raspberry Pi Pico or Pico. It's about $4 last I looked, and it's actually a true microcontroller unit. It is a single, embedded little device that would qualify as a class 2 device. So something that you might want to consider if you're interested in going down that path. Of course, operating system also plays a role, and if we're using a general purpose processor, which may not be the case with a truly constrained device, we would have to choose how we're going to actually execute our code. For a general purpose processor, like we just discussed with the Raspberry Pi Zero and the Raspberry Pi 4, then many of these operating systems would be viable for that particular device. I've actually run a number of these on my Raspberry Pis in the past, and you may choose to do so as well if you were to buy one. Now, how do we choose what type of device we use? Well, we have to look at these things and what's available, and then make a decision based on what problem we're trying to solve. We have things like swap or size, weight, and power that we must take into consideration. How are we going to communicate with other systems? That's pretty darn important. And then security. Are we actually physically constrained? Do we need to consider whether someone's just going to say, hey, this looks really cool, I think I'll take this home with me? Or is it going to be in a protected area where we don't have to worry about it being unbolted from a wall or whatnot? These are considerations that need to be taken into effect, not just the physical security, but the logical security as well. And here's another example of that. This is the chipset with a micro SD card. I'm going to hold it up here. So we've got the ability to drop our device and hopefully not break it, and store all of the information, including potentially private key certificates, on this micro SD card. So what does that mean? That means that, well, yes, there's some consideration for how data and sensitive information is stored on that device. So what are your requirements and how is it going to be deployed? Where is it going to be deployed? And what types of security considerations do you need to put into place? Timeliness is also something that is important, and I'm talking about determinism. And determinism will help you determine whether you're using a real-time operating system or a non-real-time operating system. It really depends on what the device needs to do and how it needs to behave. Do you need to guarantee that no matter what, your polling of your sensor, whatever, must happen at regular intervals, and they're measured in seconds or milliseconds or microseconds, but it must happen at a regular interval. No question about it. Well, that's determinism, and that then impacts how you deploy your device, what type of device, and whether or not you're using a real-time operating system or some other type of mechanism. And then again, we've talked about this in class. We actually use a couple of different programming languages in this class: Python on the constrained device and Java on the gateway device. But what does your team actually know, and how can they actually be brought up to speed in the development kits that are available for the devices that you're choosing? So these things all play a factor. You got to juggle all this stuff and make a wise decision, factoring in trade-offs, because sometimes you're not going to be able to go down the path that you'd like because of other constraints. And so these are things that are very basic, and they're certainly not exhaustive. There's many other things to consider, but these are some basic considerations that you would have to take in mind, to keep in mind for any device selection, especially for a constrained device. All right, let's talk about how we would access hardware using the constrained device application. And I want to stress, this is not a hardware class. We're not talking about microcontrollers. We're not talking about soldering the wires or any of that stuff. We are focused on a virtual world. However, it's really helpful to understand how the physical hardware might work notionally, so that you have a better understanding of how your software needs to be developed. So let's take a quick dive into hardware on the constrained device application. And this is important because these are concepts that you'll definitely need to know, even though you don't need to implement it. You need to know about this to help you round out your knowledge of the Internet of Things. And there you go. This isn't a hardware class, but it's really helpful to understand how hardware and software work together to make edge computing actually work or not. Hardware integration is completely optional, but the knowledge that I'm going to express now, or the information I'm going to express and the knowledge you'll glean from that should be something that you want to keep in mind, and will certainly potentially pop up on the quiz, okay? All right, so I'm going to provide a couple of links down below. You've seen this before. I'm going to focus on Python and Raspberry Pi for this particular set of examples to kind of help you better understand some of the hardware considerations that you may want to keep in mind if you're actually going to implement or use your own hardware. So remember the Raspberry Pi, we talked about that at length, and here it is one more time. This is a Raspberry Pi 4 wrapped in an aluminum chassis, which is actually serving as a giant heat sink for the device. And so all I want to show you here is that these are a couple of pictures that I took of one of my other Raspberry Pis, a Pi 3 specifically, that shows how you have access to the general purpose input-output and the inter-integrated circuit bus, the serial peripheral interface bus, the camera bus, and the display bus. You probably are already familiar with the Raspberry Pi, so I don't have to go into detail, and you can certainly check out the link below and learn more about this particular device and the entire family of devices. They even have a keyboard now that has an embedded, I think it's an embedded Raspberry Pi 4 in this keyboard device that you can buy. The point is that there are lots of ways to talk to Raspberry Pi hardware. And again, this is not a class on Raspberry Pi. I just want to call this out because it's a $35, $36 fully loaded. Oh, that's not the right word. It's a $35, $36 computer. It can certainly act as a desktop that has some limited processing capability and whatnot. But you can absolutely use it with a monitor and with a keyboard, with a mouse, and do quite a bit of interesting things with it. So you can actually use it as kind of like a mini workstation and so forth. And it's also super convenient because, as you can see from these pictures, I've got lots of ways to plug things into it. And that gives me a lot of flexibility for experimentation and so forth. So let's talk about that. There are lots of libraries available to help you do this type of work and talk to the GPIO using Python, or the I2C bus using Python, for instance. You can even talk to these buses using Java if you would like, but we're going to focus on Python. So let's actually take a look at how you might integrate with Raspberry Pi using the general purpose input and output bus. So this is a very straightforward way to connect physical things into the device and actually read data from them, or trigger an LED to go blink on and off, etc., etc. First thing you need to do is, well, read the documentation. Read the fine manual because it's there, and just check it out and read through it, and they'll tell you all you probably will need to know about the GPIO written by the people who actually designed it. So that's really a helpful place to start. The next thing to do, of course, is to decide how you want to address the pins, meaning you need to know, well, which number pin are you going to actually talk to? There are two ways to do this, using the Broadcom SoC channel number or the Raspberry Pi header pin numbers. It's up to you. You just have to tell the library which mode you're going to use. It doesn't really care. Just tell it, say, I'm going to use mode board or mode BCM. Okay, done, fine. And then the next thing to do is to determine from the pin that you want to use whether you're going to configure it for access, or how you're going to configure it for access. Now, there are a couple of examples that I've shown below where you can set up a list of pins for input, and you can set up another list of pins for output. And so, and you can even set it up with an initial value if you would like. These are all things that are built into the GPIO library, which, by the way, if you're using the if you're running Raspbian, which is an Ubuntu derivative, on a Raspberry Pi, the GPIO library should already be part of that operating environment. So here's some simple examples of what you can use. Again, these are just like literally simple 1 or 2 lines of code types of examples, but you can see how you can actually access the GPIO. Once it's provisioned, then you can start to add events so that when a certain type of event occurs on a particular pin, then you can register a callback function that will be called based on the values or the parameters that you specify, which is a really powerful way to say, hey, you know what? If the pin over here falls below this, then, or if it starts to fall, or if it starts to rise, I want you to call back to this function And from there, you can actually do a bunch of other processing and so forth. So again, one line of code, and then you write your function that will handle that, and you're generally done. So you just have to integrate it with the rest of your application. Let's take a very simple example. Let's say that you want to blink an LED. Well, I'm going to give you a very, 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 very simple example, and it's not necessarily designed to integrate with everything you've been doing, although you certainly can integrate it with your tasks and so forth. But the first thing to do is define what is your kind of high-level problem. Well, I want to blink an LED. Okay, well, that's pretty straightforward. What other context can you provide? Well, more specifically, I want to blink an LED at a regular interval when something happens. Well, that gives me a little bit more detail, and now I can use that to actually define an outcome. So my outcome is an LED that's connected to the GPIO on a Raspberry Pi will flash on or off at regular intervals when a software event is received within the application. Specifically, I should define that and say, whenever somebody presses this button and holds it, a green LED will flash every second, on and off. And as soon as they release that button, it will stop. Okay, the outcome for me is that, okay, well, it functions. Okay, that's pretty obvious, but that's not really the outcome. The outcome is that the reaction of the system to a mechanical input is successful. And so that is really what I'm after. Here's some sample code. And we've gone through this in class as well. This is a simple class that actually inherits from thread. So basically it is a thread. It inherits it imports the GPIO library that I'm showing here in the third line of code. And it literally is just setting a couple of simple parameters. It says, hey, I'm going to use GPIO pin number 17. I'm going to use the BCM mode. Okay, fine. I'm going to set up that pin to be basically out for output, meaning I'm going to send voltage to that pin. So I'm provisioning the pin and it's all good. Then the next thing I do is as soon as the enabled LED flag is set, I'm going to go through this cycle. Now, here's the thing. It's a thread, so that run loop, as soon as I call the thread and tell it to start, it's going to start calling that run loop. And I want to make sure that I actually have a little bit of a break in there so I don't like spin the processor out of control, right? So what I'm going to do here is say, well, while true, I want to do a couple of things. I want to first check to see if the LED on off kind of thing is enabled or not. Okay, well, that's set by the set enable flag method that I've got below there. And then if it is, well, I want to take that action. I'm going to actually set that pin to high, which is the highest level of voltage that pin supports. I'm not going to wait for the rate in seconds. I'm going to hold that value for a certain period of time, and then I'm going to switch it to low, which is 0 volts. And so basically it's going to turn it on for some number of seconds and then turn it off. It's going to turn it on for some number of seconds and then turn it off, et cetera, et cetera, et cetera. As part of that loop, I've got this wait. So whether or not the LED is enabled doesn't really matter. I'm still going to have this wait for rate in seconds. And that's really important because, again, it doesn't really matter whether I'm enabling the LED or not enabling it. I want to pull, wait for a second, pull, wait for a second, pull, wait for a second, et cetera, et cetera, et cetera. If the LED is enabled, then I do this other thing. If it's not, I just kind of keep doing this wait. That's it. And that's all this really does. Again, you can see that there's like, 4 lines of code here, really. Set the mode, set up the pin, set the voltage high, set the voltage low. That's it. 4 lines of code. All right, what about the I2C bus or inter-integrated circuit bus? Well, let's take a look. The I2C bus is a spec that is now managed. You can see it's by, I think, NXP Semiconductors. I've got the link down below. Definitely want to check out that PDF file because it provides the specification for the I2C bus, which is really important because even though you're not going to be implementing hardware or talking to hardware in this class, you do need to understand the specs. So for the quiz, you'll need to know this information. Let's take a quick look at what the I2C bus is all about. The I2C spec specifies basically a two-wire physical bus. There's a clock line and a data line. There's also a ground. So it's 3 wires, but it's really 2 wires in terms of the protocol definition. The primary and secondary config determine how it behaves. The primary controls the clock line. The secondary is actually the device. The primary has to issue a start sequence. Then it reads data in 8-bit sequences, and then when it's done, it sends a stop sequence. Basically tells that secondary, I'm done. I'm not going to be reading data anymore, so don't make it available. Most of the I2C buses that you'll deal with are probably going to be 7 bits addressable, but there are others that are 10 bits addressable. And that means that if we have 10 bits of availability, that's basically 2 to the power of 10, right? So we actually have potential of, what is it, 1024, 1028? I think it's 1028, right? 1028 potential unique addresses, but realistically, you've got about 20 or so that are reserved, so it's about 1008 that you have available to you with a 10-bit addressing. Of course, with 7 bits, it's only 128, and there's some reserved there too. I don't remember if it's 8 or something low or something lower, but basically you have a maximum theoretical number of addresses with 7-bit addressing of course, 128, 2 to the power of 7. So what does this mean? Well, let's take a look at the spec in detail. Figure 4-5 has this represented here. As you can see, total bus lines are 2. Again, we're excluding the ground, even though the ground is super important. We have how many bus speeds? We have 5 different bus speeds, but notice that 4 are bidirectional, meaning I can use both wires to perform, rather I'm using 1 wire to receive data, or rather 1 wire for the clock and the other wire for the data. Ultra fast mode allows me to use unidirectional capability to expand the speed of the bus to 5 megabits per second. So I can basically go from 100 kilobits per second up to 3.4 megabits per second using standard mode to high-speed mode in a bidirectional manner, or I can use a unidirectional bus and get up to 5 megabits per second theoretically. It's a synchronous communications type. It uses serial communications or for data transfer. And again, the number of primaries is theoretically unlimited, although the number of secondaries is limited to 1008 in 10-bit addressing. How do you use it? Okay, well, this is a great question. If you're using Python, you can actually use Java or C, C++, and actually some other languages, I think, as well. But for Python, basically what we need to do is a couple of things. And there's actually some other stuff that you would need to include in your installation as well, which I'll get to in just a moment. But the 2 primary ones are Python-SMBus, and then for convenience, something called I2C-tools, which gives you the ability to actually use command line application to check what's already registered on that I2C bus. And there's some links there that you can check out. Certainly, I think this is going to be really helpful for you. I would suggest that you look at these links to get a little bit more information about how to use I2C on a Raspberry Pi specifically, and how to access the different SenseHat sensors using I2C, which is, by the way, one of the optional exercises for lab module number 4. Let's take a look. How do you actually do this? Oh, this is old. So sorry, going to the next one. My bad. So first thing we want to do is define a problem and a way ahead, just like what we did with the GPIO. So in this particular case, we want to read humidity from the SenseHat using I2C directly. Now the SenseHat does provide, there's actually a couple of libraries that we can use and just write a single line of code to access humidity value from the SenseHat. But why do that when we can write 30 lines of code to do it ourselves, right? Right. So we can actually write our own code that talks to the I2C bus that will then read different 8-bit values out of a bunch of, well, 8-bit registers on the Raspberry Pi, and then we can glom them all together, perform a calculation, and derive a 32-bit value float that represents humidity. So how do we do that? Well, let's take a look. first we have to enable the I2C bus on the Raspberry Pi. We can do this in one of two ways. We can use rasp config and then go through this process that I've outlined here, or you can actually just edit boot/config.txt directly and add these two dtparam values or settings in. Now, I suggest you simply use rasp config. It's going to make your life a lot easier, but you can, if you're feeling brave, edit your boot config.txt, understanding that if you mess up your boot config, you could basically mess up your install and you may have to start all over again. There's an additional set of packages that you'll probably want to have installed. There's actually one specifically for our purposes because we're using Python 3, and that would be Python 3-dev. So make sure that you install that as well so that you can, in fact, program to the I2C bus. Once you've done all that stuff, now your I2C bus is enabled. Raspbian understands that you can talk to it and all this stuff. Well, you got to power off your device, connect the SenseHat, turn it back on again. And then once you get to a command line prompt, you can execute this command, I2C detect -Y1. Why is Y1? Well, that's a great question. That's because we're actually looking at bus number 1, not bus 0. Bus 0 is reserved. It's actually been configured or reconfigured rather with modern Raspberry Pis to read the EEPROM data that sets up the hat architecture. And so you don't want to touch that. You don't want to use it at all. Stay away from it. Just use bus number 1. And bus number 1, if you have a SenseHat connected to your Raspberry Pi and you've done all the other stuff I just mentioned, will give you a reading like this should you use the I2C detect command as I just indicated. So you can see that you've got your inertial measurement unit, your accelerometer at hex address 1C, your magnetometer at hex address 6A, your pressure sensor at hex address 5C, and humidity sensor at hex address 5F. You use actually the LED, and you can use that as well if you want, but I don't go into any detail about that whatsoever. Okay, good. So the next thing you do, once you kind of got this figured out, you can see what the addresses are and stuff, you actually have to understand what sensors you're talking to. In this particular case, the humidity sensor, which also provides the ability to read or calculate temperature, is the HTS-221 sensor. And I've got the spec listed down below in footnote 418 from ST Microelectronics, TN1218, Rev 4 technical note. That is, they make publicly available. It's their stuff, of course, but you can use that to reference and understand how the HTS-221 sensor actually works. Wow. Well, that's an awful lot of code. And you're right, it is. So it's probably a lot easier to write one line of code, right? Yes, it is. But where's the fun in that when you can use the I2C bus directly, right? Well, let's take a look at what this looks like. So if we read another spec provided by the same company, specifically on the HTS-221 sensor, then we'll see that we've got a bunch of information on how we can interpret humidity and temperature on that particular sensor if we're reading the addresses from that device directly using the I2C bus. Wow. So this, folks, is a very, very basic dipping our toes into the embedded waters, if you will. And this is where the rubber hits the road, so to speak. This is how you can actually read data from a sensor and make, well, some sense out of the sensor data. Let's take a look. So we start off by actually setting up the entry or the opening address, the opening show, if you will. This is going to be hex address 5F. And as we know from this reading right here, 5F, good, we're right on target. We can actually double check that with the specification for the SenseHat, which is also posted online at the link below. And then we know that 5F is the one that we want to start with. We need to initialize our SMBus library, as you can see here, and then we're going to write our first byte, say, hey, you know what, we're going to actually tell you, the device that's connected here, that we're going to start reading some information, 8 bits by 8 bits. The next thing we want to do is actually set two different coefficients. Now, these are already burnt into the particular device, so these should never change, but we still need to get them because we effectively need to read these two values out of these two addresses and divide them by 2. And that's what we can do by just shifting everything by 1 bit. That gives us the same representation as divide by 2. And because we're doing bit shifting, we might as well just do division by bit shifting as well. And so we end up with the values that we need for coefficient 0 and coefficient 1. The next thing we can do once these are set, because they won't change and they are basically going to be living as is for the life of this particular application, we need to call our generate humidity function. Now, again, we can integrate this very easily into our existing tasks. We change the method name, and as a return value from generate humidity, we can just say generate telemetry or get telemetry, right? And that would give us our float value, but we have to do all this stuff first. So what does it mean? We've got to read a bunch of values. We have to basically calculate what the first one is. We have to read a bunch of values. We have to calculate what the second one is. We have to basically calculate the least significant byte, the most significant byte, and then we need to calculate our out value. Once we have that, we can now calculate our humidity by plugging these all into this algorithm that you see below, which again is basically provided for you in the manufacturer's specification, because they know that people are going to be writing code to talk to the sensor that they manufacture. So they make a spec available, say, okay, if you want to talk to the sensor, here's how you do it. And so this is what you do. This is basically my interpretation of the C code that they embedded in their instructions, but written in Python, so that you can see how you might read humidity from all of these different locations and ultimately calculate the float value that represents something a human can understand. Okay, so with that being said, that's it for now. We still have a lot of stuff to cover, so let's continue blazing ahead. Hopefully you're not bored yet. This is unfortunately a long video. We're already an hour and 6 minutes in, and we probably have another like 30 minutes to go. So stay tuned, there's more. All right, class number 4, we are going to continue on with integrating with the SenseHat emulator. And all of this stuff, by the way, is online in my GitHub repository. You've got the instructions laid out, so I'm going to blast through this pretty quickly. So let's actually get started. The SenseHat emulator is actually required for this class. So even if you have physical hardware, I still want you to learn how to use the emulator so that you can run some of these experiments without having to rely on physical hardware. When you get it up and running, this is basically what it's going to look like. And again, the instructions are provided. I personally think it's easiest to run in a Linux environment. Some may choose to run it in Mac or Windows natively. I actually do most of my work running Ubuntu 20.04 long-term support within a Windows subsystem for Linux version 2 environment. So I basically run a version, or rather I run a full version of Ubuntu headless within Windows, but I have graphical abilities because I'm also using an X11 interpreter or X11 server running in my Windows environment that allows me to launch this as a graphic window within Windows from a Windows subsystem for Linux Ubuntu 20.04 long-term support terminal window, also running within Windows 10. It's a lot of stuff, but you can do it. I do it because it's convenient for me. I like to have a single keyboard and all this stuff, and I don't like switching between systems and operating environments and so forth. And this gives me more flexibility in how I actually work. And so you can choose to do that yourself, or you can just run a Ubuntu VM, and that would basically make some things a lot easier for you. And some of you may choose to do that. I think some of you are. So that's totally fine, up to you. So how do you install it? Well, check out the instructions. I've got them linked there. Remember that an X11 display server will be required if, well, actually, we're required anyway, but if you're running on Windows 10, you're going to need to install that separately. All right, lastly, let's talk about hysteresis. I talked about hysteresis a little bit before, and I could get hysterical about hysteresis and talk about the history of hysteresis. I'm just kidding. I'm not going to do any of that. What is hysteresis? It's just a lagging effect. And well, as I said here, a resultant value that occurs when a force is applied. So in a control system, we can use hysteresis as a function, if you will, to filter input, say temperature, for instance. And the reason we do this, let me blaze through all this stuff and say, for instance, if I've got a temperature reading, and the temperature reading, like you saw in the noise, right, is fluctuating between, say, 21.0 and 22.0. Now, as a human, yeah, I can definitely feel a difference, but let's just say that there's some fluctuation in how the sensors are reading, or let's just say that there's a cold spot in the house or something like that, or maybe somebody walks past and it causes a rush of warm air, and then the temperature reading goes up by half a degree or whatever. The last thing I want to do is every single time that temperature reading moves like a quarter point is tell the heating system to turn on or off or something, right? Because it's going to fluctuate so much. I could potentially be sending the heating system a signal to do something that's pretty expensive, like turn on the boiler, heat up all this water, use a bunch of fuel, circulate that hot water through, one or more zones. That's too much. So I want to use hysteresis to my benefit. And I basically want to let that function level out. I want to delay my interpretation of it. So I'm going to let it settle first and then make a decision. So once I see the average basically exceeding a threshold, that's when I want to take the action. But until I get to a certain number of readings that exceed the threshold or at the threshold that I care about, at least for temperature, I probably don't want to take an action. Now, for other things, I probably do. If I'm like reading water level or something like that, or let's say I'm reading like temperature or smoke, then yeah, I may want to be a little bit more fidgety and actually trigger something quickly. It depends on the problem I'm trying to solve and, of course, the urgency of that problem. Is it life-threatening? Well, I certainly want to be more proactive. Is it something that's more related to just general comfort? Well, maybe I do want to expand that time frame a little bit. So anyway, this is a process by which I can avoid triggering something that really doesn't need to be triggered right away. But even if the input data is telling me that I might need to. Hopefully that makes sense. All right, so let's take a look at the design diagram. So this is what it looks like. Notice that they look very, very similar to the design diagrams in lab module number 3, but in this case, we're not making any changes to our application infrastructure. We're simply tweaking our sensor adapter manager, our actuator adapter manager, and we're adding the emulator tasks, which look very similar to our simulator tasks. You can see in the detailed design here that this actually is the case. Notice that we've got a corresponding emulator task for every sensor task. However, for the actuators, I've actually included one additional one. This is for the LED display that would be used to control that 8x8 matrix on the emulator that I showed you a moment ago. And so you can see how this all gets integrated into your system. And if you choose to use GPIO or you choose to use actual hardware using the I2C bus, you can still factor all of that functionality into this same exact design, which makes this design relatively flexible for the purposes of future projects and whatnot. And that's really the purpose behind it. Okay, that's it for class number 4. Now we're going to get back into data management and reintroduce the gateway device application. Let's take a look. All right, class number 5 is about integration standards and data management. I'm going to blast through the standards because you already have this documentation. I posted it in Canvas and I've talked about it at length, but I will touch on it briefly just so you have a refresher on all of that information. So we're going to talk a little bit about communications protocols, some data standards, and then get into the implementation for your data management solution. All right, messaging and connectivity protocol considerations. There's lots of ways to view a protocol stack. And by the way, you really should read the preface to part 3 of my book, which is already posted online on O'Reilly Media. Please check it out because it covers some of this stuff there. And so it'd be good to use that as a refresher. All right, so key things to keep in mind. You've got your physical medium and your connectivity. You've got your transport management, which sits above that, and then your application and data management that sits on top of the transport. Now, I'm grossly oversimplifying this, But this is all to say that for our purposes in this class, we're going to focus on that very top level, the application layer. However, we are going to talk a little bit about the physical connectivity and a tiny bit about the transport layer as well. So before we do all that, let's actually look at 3 different views. They're not designed, by the way, to be related to one another. They're just 3 different views of a protocol stack or a typical protocol stack. So first we have the ISO OSI 7-layer stack reference model, which is ISO 35.100 OSI. Definitely check it out. It is linked down below. Actually, I think it should be iso.org, not ios.org. Sorry about that. Oops. But that being said, it's a 7-layer stack, and the whole idea here is that each layer builds upon the one below it, and they are very, very clearly defined separation of concerns layers, meaning one layer does a particular job, the next layer does another particular job, et cetera, et cetera, et cetera. They don't bleed over into one another. That's by design. The IETF Internet Protocol Suite reference model, which is IETF RFC 1122, you should know that as well, and is linked below also. This represents a 4-layer version of a protocol stack where we have our link layer down at the very bottom. This is our physical medium up to our IP layer, which provides some kind of connection-less internetworking services, basic services to move data from point A to point B. Above that, we have the transport layer, which provides some kind of negotiation, communication services that permit some type of handshaking and whatnot. We've got TCP on one side, which provides that advanced handshaking. Hey, I'm going to send you a message. Okay, awesome. Send me a message. By the way, I'm going to send you a message that is so long and has all this stuff. And the other guy says, okay, I'm ready for you to send me that message that has this much stuff and all that. And I said, all right, you ready for me to send it? I'm ready for you to send it. Okay, here I'm going to send it. It's like, okay, I'm ready to send it. Here you go. And it goes back and forth like that. It's not obviously not that dramatic. I'm joking, trying to be a little bit glib here because it's a very dry and boring lecture that we're already an hour and 16 minutes and 25 seconds into. But that being said, we've got a 4-layer stack that we have defined for us, which is really helpful for us to understand a lot of the protocols and whatnot that are shown here. Now, this is, again, not to be correlated with either one of the previous diagrams in any way, shape, or form. This is something coming out of the Industrial Internet Consortium, IIC's connectivity framework, and it shows a view of different connectivity standards that are often used in an industrial context. And you can see that we're actually showing a couple of protocols that we're going to talk about in part 3 at the transport layer, but really MQTT and CoAP are not transport protocols per se. They're more application layer or session layer protocols. However, they have transport layer like characteristics because of the way that they operate. And so we can kind of theoretically say at a transport layer, we've got these things, but the important thing is that they both sit on top of TCP and UDP. So again, we're not comparing with this, but for our purposes, we're using these protocols at the application layer. So hopefully that disambiguation makes sense. I think at this point, you probably know that there are lots of different ways for devices to communicate at the application layer, as well as all the way down to the link layer. And as you can see, there are a number of different protocols and communication standards that are available for consideration. By the way, the Industrial Internet Consortium's connectivity framework provides a kind of assessment, a set of assessment criteria for various protocols that you can use to help determine whether or not one is appropriate for your particular situation. And that would be definitely something to keep in mind, and you should absolutely have at the ready. You can download it on their website. Just make sure you're paying attention to their usage license and so forth. Okay, so with that being said, we've got a number of things here. You've got 6LoWPAN, Bluetooth Low Energy, Wireless HART, Z-Wave, Zigbee on the left-hand side. We have other things like 5G all the way down to the waitlist on the right-hand side, and I'm not going to talk about those. Yeah, we could, but I'm not going to right now. Incidentally, if you want to learn more about these protocols, if you haven't already, you may want to consider pre-ordering Dr. Herrera's book on Internet of Things or IoT communications paradigms and protocols. got a pre-read of it. It is really, really well written. I found it to be super helpful in my own understanding, and you may as well. So if it's something that you're interested in, you may want to check it out on the Springer website. So that's something to consider. All right, let's take a really quick walk through a few of these protocols, the ones on the left-hand side, and then talk about some data management standards, then finally get into our own protocol development. Okay, Z-Wave is listed here. Again, I'm not going to talk at length about this, but you should know this spec. You should also know Zigbee. And again, it's referenced in the documentation like this one here. You can review this online through Canvas. All the stuff is posted for you. Make sure that you know how to access these links. It's very important. Same for wireless HART and Bluetooth Low Energy. And finally, of course, 6LoWPAN, which, excuse me, by the way, has our friend Thread associated with it. So this is something, again, all of these protocols you should be familiar with. Make sure, excuse me, that you understand the spectral range as well as the bandwidth and the communications range and the maximum number of nodes to at a minimum. But you should certainly know the basic capabilities of these protocols. Okay, all right, hopefully that makes sense. All right, let's talk about some data messaging standards. One, M2M. Well, I'd love to spend more time on this as well as OPC UA, but we don't have a lot of time in this class to do that. So I'm going to provide you just some links that you really should be familiar with. You should definitely check these out. Be familiar with what this particular standard provides as well as OPC UA. Note that OPC UA actually supports a couple of different communications types, including request response as well as pub sub, which I'll talk at length about in part number 3. Some other standards that you should be familiar with. You don't need to know all of the spec detail for each one of these, but definitely know what they are and what they're important for. How do you incorporate these? Well, I told you already that using the IIC's connectivity framework guide can be helpful in assessing what you should actually be using going forward, but you ultimately need to decide what connectivity problem you're trying to solve and what are the available options to solve that problem. Then my suggestion, and I found this helpful for my own use, and certainly when I'm working with clients, this is usually a very helpful exercise, is to run a proof of value experiment using what we understand as the problem. We find a slice of that, and we basically move forward with a very inexpensive proof of value to make sure that, okay, are the things that we thought true still true, or do we need to make some adjustments or whatnot? This is, again, a very helpful way to kind of kick the tires, if you will. All right, here's one integration example that I've used in my house. I've been running something called Home Assistant for many years now. And this is just one screenshot from my implementation of this. You can see that I've got actually a number of Z-Wave devices, and I'm reporting back on battery capacity remaining for 4 different devices. I also have links into my own personal website as well as weather service. And so I'm using just TCP/IP for those connections and so forth. And you hear my cat meowing in the background. So with that being said, I may step out just to let him in for a second. So I will do that. Bear with me. All right. My cat's now in, and I think pretty happy that he has access to my office. Okay, with that being said, there's a bunch of stuff you can do with something like Home Assistant. You can also use something called Cura, and there's other tools that you might want to consider as well. Something called MainFlux, for instance, which gives you the ability to run an entire advanced gateway capability and do some analytics and so forth right there within the engine. All right, that is it for now. Let's move quickly ahead into integration standards data, specifically data management in your own data creation functions. All right, building your own data payload is fun, and it can be frustrating because we have to deal with things like character encoding and stuff like that. We can make it a little bit easier though, because I think I provided some guidance for you in the documentation in the GitHub requirements on my Kanban board. So check those out for lab module number 5. It's definitely important for you to understand how these work though, because these questions will come up on the quiz. All right, remember we talked about a lot of different things that are necessary in a message for context purposes. We got to understand where something is coming from and what it is. Otherwise, getting a value of like 22.3 means absolutely nothing. We definitely need to know what type of device it is, what type of sensor it is, and where it's located. We also need to know the timestamp, because getting a value of 22.3 at midnight may be very different than getting a value of 22.3 at noontime. All right, so with that being said, here is a representation in figure 511 of what that whole payload looks like in JavaScript object notation, or JSON. And so this is basically just the object that we stored, a sensor data object, completely transformed into something called JSON. And that's what it looks like. It kind of looks like XML, but it's not really XML, right? It's actually just a bunch of key value pairs, but we can actually stagger, we can layer these into a tree structure if we really want to. So we can kind of have XML-like capability within this, except we're not going to use that. We're going to use JSON instead. So if you look at this, doesn't it seem like these are a bit too banal for our purposes? And you'd probably be right, they are. But for what we're doing, it's actually very sufficient, because we don't need a bunch of extra stuff. We don't need any additional descriptors and so forth and so on. We can actually make do with just what's here to solve the problems that we have for this particular class. So let's avoid overcomplicating it, at least for now, and leverage it for what it's good for. That is providing some context around data, enough richness so that we can make a decision what to do with that data when we receive it at the gateway device app or in our cloud service. But let's stick with the following guiding principles, which includes using ISO 8601 for time format, and of course, meaningful labels where appropriate. For example, if we have latitude, longitude, and elevation, let's use those, and let's use the decimal version of those so that we can better interpret that information. Okay, what about persisting this information? Now, that may be helpful. Bear with me, I'll be right back. Cats, you know, they want to come in, then they want to go out, then they want to go out, then they want to come in, and then they just can't make up their minds. All right, so you may hear a meow again in the background. Sorry. Anyway, let's get back into device data persistence, or specifically on-device data persistence. So what is that all about? This is just a way for us, specifically within the gateway device application, to store information temporarily so that we can replay it later if necessary. It's also helpful to have some logging capability so that the gateway device app, which typically will have a lot more storage, or the gateway device itself will typically have much more storage than a constrained device, can actually store a bunch of information for accounting purposes and so forth. And this could be really critically important depending on how the device is being used and in what context. So with that being said, we're going to actually talk about how to do that using something called Redis. Now, Redis is Remote Dictionary Server. It's an open source, lightweight, in-memory key value data cache, and you can download the code for many different platforms. I think I've got a link down below. You can definitely check it out and go to their website. I think it's redislabs.com, I believe. They have a commercial version as well as an open source version. For our purposes, the open source version is sufficient. It gives you the ability, again, to store data, specifically because it's a NoSQL database. What you can do is you can actually store serialized versions of your objects, sensor data, actuator data, system performance data directly in the database very, very easily. Or you can convert them to JSON and do it that way too. It's really up to you. Here's some instructions for actually installing and starting it. These are actually available within the Kanban board, so you can check them out there. I'm not going to go into detail here, but it is important that you understand how you can use a on-device persistence store to track the data that's actually coming and going and so forth, and be able to replay that later if necessary. There are a couple of libraries you can use. Now, we don't really need the Python one, although I provided some optional exercises in case you want to experiment with communicating between your CDA and your GDA using Redis, which by the way, you can do. In a real world situation, you're not going to be storing, you're not going to be running a database on a constrained device, or very rarely would you do that. So it's going to be mostly within your gateway device. So the right-hand side, right-hand column shows you an example, or rather a link to a library that you can use for your gateway device application to access Redis database. There are others as well. These are just two. You can take your pick. All right, what does this look like? When you implement your code, notice that for the constrained device app, it's going to look similar to this. You're really just adding something called data util. Data util, again, all this stuff is documented on the Kanban board, gives you the ability to convert your sensor data, your actuator data, your system performance data to JSON and back again, which is really convenient because once it's in JSON, now I can pass it to other systems and they can use their own JSON interpreter to basically reconstitute that into their own environment. This is the UML, and you can see it looks very, very simple. We're going to use a singleton pattern for the data util. You don't have to, but it's convenient, and I provided one for you. This would be a meta class, in fact, in that you can use it as is if you would like. On the gateway device app side of things, you'll notice that this is looking strikingly similar to Lab Module 3 with the constrained device app, except there is no sensor data or actuator data manager. And that's because there is none. There is a persistence client adapter, however, because again, the gateway device app will talk to a data store locally running on its system. And here's the UML for that. You can see that we're introducing system performance data here, which the system performance manager will now use, which is why it's colored green, being a modification. We are now swapping out its role with device data manager. So the design is very similar to the constrained device application, where the GDA talks to the device data manager instead of the system performance manager, and the device data manager creates and manages the instance of system performance manager as well as the persistence client adapter. The device data manager now has the role of orchestration engine, and you'll see as we go through the remaining classes how important that is in terms of deciding what to do with the messages that are flowing into it and what messages it needs to send out. Data util actually has 4 different converters, one of which is something called system state data, which by the way is optional. You don't really need to create it. I mean, you do because the test won't run without it, but it's not something that you'll probably find much use for. I created it for my own solution because it's helpful to have a single object that I can dump all of this information in. And then if I choose to use a batch upload to the cloud, basically once every couple hours or whatever, or maybe once an hour, or even once every 5 minutes or something, I have a singular object that contains all of this information. Just makes it convenient for me to do the job that I want to do, whether I want to stream data or batch upload data to the cloud. Okay, and here's the listing of all the steps. You can check out Lab Module 5 on your own, but do keep in mind that the CDA and the GDA both have requirements for this particular lab module. So folks, that is all I have for you. This is the end of part 2 and class number 5. So I hope this is helpful in helping you prepare for the upcoming quiz.